Hi everyone. Today I will be presenting the Sachdev-Ye-Kitaev Model, which is a system of Majorana zero modes with random infinite range interactions. This simple quantum mechanical model exhibits deep connection to black hole physics through the holographic duality. The background of the slide just depicts an artist's representation of the universe as a hologram. I hope you find this topic as interesting and fascinating as I do. We first discussed the concept of quantum holography, also known as the ADS-CFT correspondence, which will motivate the need to study the SYK model as a holographic dual of extremal black holes. I will be discussing the SYK model in its original form using Majorana fermions. I will also be going into the details of the structure of the model and its two-point functions that act as bilocal fields. In the large N strongly interacting limit, we obtain very interesting results that exhibit conformal symmetry. The emergence of such symmetry alludes to the deep connection of the model to black hole physics and holography. I will briefly discuss another version of this model which uses complex fermions instead of Majorana fermions and show how it leads to similar results. Finally, I will be discussing experimental proposals for the SYK model in a solid state system, hence black hole on a chip, focusing on one particular proposal involving 3D topological insulators. In modern physics, we know that the theory of the very, very big is inconsistent with the theory of the very, very small. General relativity is used for gravity, while quantum mechanics is used for explaining nuclear and electromagnetic forces. Now, they are both valid and proven time and again within their own field of applicability. However, the issue arises when we want to operate at extremely small scale with extremely strong gravity, such as that within a black hole. For instance, according to general relativity, an event horizon of a black hole is a surface of no return. However, when treated quantum mechanically, we get Hawking radiation, which leads to theories stating that black holes behave like thermodynamic systems having entropy, charge, temperature, etc. In the string theory framework for quantum gravity, black holes are considered as interacting many body systems obeying usual relations of thermodynamics. This motivates the need for a microscopic theory of black holes, which is in its most developed stage in the form of the ADS CFT correspondence. Let's imagine a two-dimensional surface which depicts our universe at a given time. We can stack up as many such 2D universes vertically for different values of time. This would result in the vertical time axis as a third dimension, creating a bulk three-dimensional space from a two-dimensional space. This is the basic concept of the ADS CFT correspondence, where ADS stands for anti-de Sitter space and CFT stands for conformal field theory. In a more formal language, we say that a quantum gravity system in a d plus one dimensional spacetime is equivalent to a many-body system defined on its d-dimensional boundary. The cartoon on the right shows how cows at different distances in the ADS bulk space correspond to many cows of different sizes at the boundary. So here, string theory and quantum gravity in d plus one dimensions translates into a quantum, not a quantum, basically a cow many body system without gravity in d space dimensions. And this is relevant to us because the microscopic description of black holes immersed in ADS space can be given in terms of well-known concepts of many-body physics in the form of conformal field theory. The figure on the right shows a representation of the holographic duality, where the many-body system in the form of a graphene flake in applied magnetic field is the holographic equivalent of a black hole immersed in ADS space. Subir Sachdev and his first graduate student, Jinwoo Ye, first proposed a model with all-to-all random interactions for a spin glass system in 1993. Alexei Kitaev reformulated this model for Majorana fermions and presented it as a holographic dual to a black hole system just recently in 2015. This gave us the Sachdev-Ye-Kitaev model. So let's discuss the specifics of this model. We start with a system of n Majorana fermions. Majorana fermions are basically particles that act as their own antiparticles, exhibiting these anti-commutation relations. The Hamiltonian for the model is given by this. Here, Xi, Xj, Xk, and Xl are Majorana fermions, basically, where the indices run from 1 to n. The most important concept here is that the interactions are all-to-all and completely random. This implies that there is no concept of distance, making the Hamiltonian effectively zero-dimensional. And all the coupling constants given by J are random, real-valued, and independent. They are drawn from a Gaussian distribution with mean 0 and variance that is given by uh, this. This JIJKL squared term is the disorder average, and we will think of this J squared term with indices as an additional field in the system whose 2-point functions is given by J squared. And we will be using this concept shortly. And also, I must mention that this model is exactly solvable in uh, the n tends to infinity limit, so for infinite number of particles, and we'll see shortly how that is so. And beta j greater than 1 ensures that we are in the strong coupling limit, which also corresponds to the holographic limit. We can define the averaged fermion propagator for this model. The correlation depicts a bilocal field since it is local in space but non-local in time, or imaginary time in this case. The free propagator can be easily calculated from basic definitions as shown on the slide. Following this, we can write Dyson's equation given by this and with fermionic Matsubara frequencies. The next logical step is to calculate self-energy, which occurs in this bilocal propagator. We can draw the contributions to the self-energy as shown on the slide. Okay, let me explain these diagrams in a very intuitive manner. In the Hamiltonian, there are 4 Majorana fermions and 1 J term. The solid lines are the fermion propagators, and the dotted lines are the disorder average field. If our propagator is written for Majorana fermion, let's say I, then it can interact with the Majorana fermions given by J, K, and L, where each J, K, or L propagator is of the order n, because each internal leg is summed over n Majoranas in the system. Remember I said some time back that J can be treated as an additional field. The J with the indices is treated as an additional field. So the dotted line can be thought of as disorder average or propagator for the J field, which is of the order 1 over n cubed. Therefore, overall diagram A is of order 1. Similarly, a higher order diagram B is also of order 1. However, diagram C has fewer internal legs, as you can see, and you can check that the order of C is 1 over n, and hence in the large n limit, we can ignore C. The diagram C does not contribute. Now, to write the expression for self-energy, we need to sum over all such diagrams. People call it melonic diagrams, people call it rainbow diagrams. If you notice diagram B, you will see that it has diagram A embedded inside. In these two diagrams, all the solid lines are the free fermion propagators. If you remember, we have done similar things in class as well. But instead, if we take diagram A as a template and replace the solid lines which represent the free fermion propagator or G naught by the full Green's function. So what I'm saying is that replace G naught by the full Green's function, then you get the self-energy. So we can easily generate the full series of the melonic diagrams contributing to the self-energy if we replace the G naught by full G's. The solid lines here are the fully dressed fermion propagator. In this form, it is evident that the self-energy takes the form given by the equation on the screen. Now, this can be easily seen because the j squared term comes from the dotted line, and the three solid lines are the full Green's function. So we have j squared into g cubed. Now we go to the conformal limit solution, which is essentially saying we go to the low frequency limit. In the low frequency limit, we ignore the I omega term that was present in the full Green's function that I showed a couple of slides ago. And this is the equation we are left with for the propagator. The solution in this so-called conformal regime is given here. Unlike the Fermi liquid theory we have studied in class, this expression for propagator does not have poles. The characteristic square root singularity that you see in the spectral function in this conformal regime can be used to detect the SYK behavior in an experimental setup. The most interesting characteristic of the solution in this limit is that equations in blue remain invariant under time reparameterization, as shown in the equation for the Green's function and self-energy. Here, f is just any arbitrary smooth function. This is highly fascinating because in our equations that were derived for quantum many-body system, we are able to treat time just like any other parameter. And this property is called the emergent conformal symmetry. Now, this provides a clue as to the deep connections between this model and black holes. Remember the ADS CFT correspondence. This is the CFT. Using quantum field theory concepts, we can write a Lagrangian and corresponding action such that the equations of motion of this action give rise to the solutions we derived before. Remember when I spoke about the concept of ADS-CFT, I mentioned that slices of d-dimensional space at different times stacked together make up the d+1 dimensional bulk space. It is to be noted that the first action, the one in black, is non-local in nature. But if we need to get real correspondence between solid state side and gravity side, we need action that is local and time coordinates. It can be argued, of course, like after employing about 10 pages of hard calculations, that the dominant fluctuations of the Majorana SYK model at low temperatures are controlled by a Schwarzian effective action, which is given in blue over here. So, if you remember, we always took the low frequency limit, and when the time difference goes to zero, that it shows the deviation from that low frequency side. So we will get some fluctuations in that limit, of course. And these dominant fluctuations, like I said, they are controlled by the Schwarzian effective action. And this effective action can be used to compute energy fluctuations and hence specific heat in a canonical ensemble. Now, if you see, this blue action is now local in time. And in fact, you must have guessed that this is the same low energy action that describes black holes in ADS space. Since this effective action is used to calculate various thermodynamic quantities, we can infer that the thermodynamical quantities we obtain in the SYK model match the thermodynamical quantities of a black hole. Now, that is something I consider very, very cool. Another quantity of great interest in this field of research is quantum chaos. The classical butterfly effect quantifies the sensitivity to initial conditions in chaotic systems, where nearby trajectories diverge exponentially quickly from each other. In quantum mechanical systems, instead of trajectories, we try to calculate how quickly information contained in a perturbation spreads through the system. This is called scrambling. The out of time order correlator defined over here quantifies the quantum chaotic behavior, and scrambling occurs exponentially fast as 1 minus f of t, with the exponent having a factor of lambda L, which is 2 pi t. Now, black holes are as strongly coupled as possible. Their Lyapunov exponents, the lambda L exponents, are as large as is allowed, and they scramble information as fast as allowed by fundamental physical laws. And looking at the manner in which information is scrambled in a quantum system can provide a connection to its gravitational description as a black hole. So now it should be of no surprise that the SYK model has the property of maximal scrambling, which means the 1 minus f of t shows the exponential behavior where the exponent has a factor of lambda L. The SYK model we discussed so far was formulated in terms of Majorana fermions. Here is a version of the same SYK model, but which uses ordinary fermions instead of Majoranas. This figure, taken from Sachdev's paper, shows the Hamiltonian of fermions on the left. The correlators can be calculated in a similar manner as we did. Now, Majorana fermions have no charge, but here we define a quantity Q, which is the charge density. The correlators and the equation governing the zero temperature entropy can be calculated. Now, if one starts from the gravity side, similar correlation functions are obtained. However, on the gravity side, you would start with a metric and a Lagrangian and so on. And the equation that one would get for black hole thermodynamics for entropy is exactly the same as one would obtain in the fermion version. Although theoretically slightly more complicated than the Majorana fermion version of SYK, this model is expected to be easier to implement experimentally, And perhaps it is more advantageous since it's difficult to obtain Majorana fermions in a lab, and you cannot perform transport measurements on Majorana fermions. But with this, since it has a charge density, you can perform transport experiments on this. Although we cannot go and measure various quantities inside a black hole, but we can definitely implement its dual, the SYK model, in our labs and get black hole on a chip. However, this is not easy. The first hurdle we need to cross is getting these large number of Majorana fermions in a stable environment, which is quite difficult in the first place as of today. In a real system, we cannot hope that our Hamiltonian will exhibit four fermion terms and no other terms. In fact, a quadratic term involving two Majorana fermions will have a stronger effect than the quartic term that we need for our Hamiltonian. Hence, these bilinear terms will need to be suppressed. Then, we need these interactions to have an infinite range, regardless of the distance. Lastly, we need sufficient randomness in the coupling constants, as is a requirement of the model. Some proposed experimental realizations include ultra-cold gases or graphene flake with irregular boundaries, quantum wires, and Majorana fermions in a 3D topological insulator. I will be discussing one such implementation. Here I will discuss the proposal for implementation of the SYK model at the surface of a 3D topological insulator. The Foucault model states that the proximity effect between an S-wave superconductor and the surface states of a strong topological insulator results in a state that supports Majorana bound states at vortices. For this model, the effective Hamiltonian is shown on the slide. The first term is the bilinear contribution arising due to the tunneling between Majorana fermion wave functions. This can be suppressed by tuning our setup to zero chemical potential, which coincides with the Dirac point in such a setup. At zero chemical potential, there is no hybridization between Majorana wave functions. Mathematically, we can also say that there is an additional symmetry induced which changes this I to a negative I and removes the bilinear contribution. Now, we also need infinite ranged interactions. This is ensured by localizing Majorana zero modes in the same region of space by fabricating a hole in the superconducting layer. When magnetic field is applied, an integer number of flux quanta are trapped in the hole, and the superconductor exhibits a 2 pi n winding around the hole. In short, this creates n vortices in the same region of space. This is called vortex spinning. And of course, those vortices host Majorana fermions. So all the Majorana fermions are um, localized in the same region of space. The randomness in the coupling constants is introduced by designing the hole to have an irregular shape. This forces the Majorana wave functions to have a random spatial structure. And this, if everything goes correctly, we would have the black hole on a chip as promised. This brings me to the end of my talk, where I will summarize what we learned so far. So, the Sachdev-Ye-Kitaev model is a holographic dual to extremal black holes that reside in the anti-de Sitter space. And it describes a system of n Majorana fermions with very strong interactions that are all-to-all and completely random. We calculated the 2-point functions and the self-energy in the large n limit and found that there is an emergent conformal symmetry obeyed by the solutions. This emergent conformal symmetry is very important since because of that symmetry, we can write an effective action which is the same as the action one would obtain for black holes. Like I said, the effective Schwarzian action describes the low energy dynamics of both SYK model and extremal black holes. And we also had a brief discussion of complex SYK model and how it is slightly more advantageous than the regular Majorana fermion version of the model. And then we discussed proposals for physical realization of the SYK model, focusing on the implementation inside a approximatized three-dimensional topological insulator. And finally, the references for my talk are displayed here. The links are given in the description below. And thank you all very much.